And I think we uploaded quite some nice examples, and I will go through 3 of them today, showing you the tool. And I really want to encourage you to follow what I'm doing, or do it later yourself. As said, we record this, we will upload this at some point, and then you can also have a look at the recordings or ask us again. Indications for disorder: anisotropic or very large ADPs. Yeah, if you have 2 different orientations or positions when atom can sit and you only refine one, you often get a very big ADP which tries to cover the density of both, or flattened prolate ADPs, so which are not spherical anymore. That can be also a very nice indication. Low site occupancy. Yeah, if the site is not fully occupied, which for some solid compounds, solid state compounds can be, but for carbon, for example, this cannot be, of course. Yeah, why should there be only 30% of carbon? Large residual electron density peaks. Yeah, if you see additional peaks which are quite strong and not noise, then this is maybe a not refined atom position. Quite often you see ghost molecules, moieties in the residual density, like if a benzene ring and you see Q peaks in the 6-fold manner of the benzene ring in a different orientation. Well, that's of course an orientation you've also refined. And what you also see quite often is diffuse signal on your frames. Yeah, because crystallography is based on periodicity. So the structure factor generated by your structure is continuous. Yeah. And you only see reflections at certain points, which we call Bragg reflections, because the periodicity only allows us to see this signal at certain points. Yeah. The more you deviate from the strict periodicity, the more parts you see from the F function, from the structure factor function. That means the broader, the more smeared, the more streaks you get in your diffraction pattern, the more sure you can be that there is a lot of disorder going on. We will today only talk about molecular disorder you can refine, of course. Disorder is very typical for very flexible molecules. For example, if you have a butyl chain, which is by its nature quite flexible and can take different orientations. Spherical molecules like DCM or chlorate, since they're kind of spherical, they tend to rotate, or molecules with cavities in their structures, like you quite often have for MOFs, for example. And I think every MOF crystallographer know what I mean. Okay, static disorder, 2 or more distinct moiety molecule positions. This you can model, of course. Dynamic disorder, a quick movement, yeah, shorter than the observation time of X-rays. The density is smeared, shows the average. That's hard to model. Yeah, cooling may help to reduce the thermal movement. Full disorder, you can't do anything. Yeah, if you don't see positions, you can't refine them. Often it's just a big blob. This is what we have squeeze for. And periodic disorder, that's what I referred to in the beginning. There you have to make sure you properly have your unit cell assigned. It's not disorder, it's missed periodicity, superstructures, incommensurate structures, or so on. Yeah. Today, we will only deal with static disorder, so different positions you can actually model with your refinement program. 2 additional phases I want to show here. The first one is Christian Hübschle, the author of Shell-Ixle. Shell-Ixle is our refinement plugin. Shell-Ixle, of course, also exists as a standalone, but it's also our refinement plugin. Christian is working for Bruker for a while already and putting a lot of effort in improving the refinement plugin so that you find everything to model disorder you need. The other phase I want to show here is Daniel Kratzat. He wrote, among other tools, DSR, Disorder Structure Refinement. It's an additional tool which you can use as a plugin for Apex, which is a very handy tool, a fragment database where it's very easy to put fragments on density and model solvents or disordered parts. Also, Daniel is working for Bruker, which is quite nice and putting a lot of effort in improving things. Okay, I will use disordered structure refinement from Daniel a lot. DSR, you can download it for free. You just install it with defaults, close Apex, reopen it again, and then it's available as a plugin. You can download it for here, cite this one if you use it. And I think that is all I want to show. No, there's one more slide. I have 3 examples, or we put together 3 examples. Disordered moiety, that's this guy here. It's just a standard molecule where you have one part of a molecule being disordered. This is what we will start with. A very nice example. The second one, also pretty typical, is this guy here. The molecule itself is ordered, but the solvent is disordered over a symmetry center. So this can be quite tricky, and that's why we want to show it. And the last one is this guy over here. This is a metal organic complex where the ligand is completely disordered. Pretty bit tricky to do, but this is also something I want to show. On the share for this workshop we created, you find 2 additional data sets. One is azolene, that's a whole molecule disorder. So there's one molecule in the SML unit and it's completely disordered. So that's a nice example to practice. And there's another one, Karsten, is it? I think it's loratadine, right? Loratadine is a side chain disorder, so rather a simpler case, but also a nice case to practice. And again, you need to practice this. Yeah. So Karsten already put 2 both references. Yeah, 2 very nice references on how to model disorder in there. One is from Peter Miller, the other one is from Daniel Kratzert, right? Among others. Yeah. Read through that. They give very good guidelines on how to properly deal with disorder because there are many things you should keep in mind. I think that is all I wanted to show in advance. Of course, we will not stop here. We will now go over to the hands-on part of this workshop. I will work through the data live. If you follow and think I'm too slow or too quick, just let me know and we can adapt the speed, of course. At the moment, are there any questions I need to answer? No. Happy audience is always good. So I will open Apex. So that's what I left open from the last workshop. So I will completely close that one. Look safe. Okay, then let me quickly switch off the camera. Okay, the first example, we will create a new project. We start with a blank one, empty one, and navigate to the basic disorder. Choose, give it a nice name. I usually take the folder name for sake of consistency. Already exists, yeah, because I used it for a workshop already. Then we'll just reopen it. Basic disorder. Good. What do we have in the work folder? You will have there disorder, HKL, and ins, and a P4P, and a solution for cheaters. Of course, we do not check the solution for cheaters. We do it ourselves. So we will, of course, not process the whole data. What you want to do is you want to solve the structure. So we click on Find Structure, Solve Structure. It automatically loads the right files, and we just click on Solve. For me, it takes a few seconds because Zoom and video and Studio and Apex is a bit too much for my computer. But there we are. We don't want to mess with space group today. The right space group is PBCA. So this one, we close it and directly switch over to the refined structure plugin. The right solution is put in PBCA. That's the molecule, and it's very obvious what is wrong here. So the whole molecule looks already pretty nice. Only this guy here is pretty ugly. So this is what we have to properly treat now. So the most powerful tool for this order refinement is your brain, because no computer can tell you what this is. You have to find it out yourself, or you know it from the synthesis. So in this case, it's obviously some kind of cyclohexane or cyclopiperidyl, so piperidyl moiety. So it's one orientation, and the other orientation we have to look for. So the first thing we do is we remove all hydrogens, if there are any, and make it isotropic, because the anisotropic thermal movement can conceal Q peaks. So this is now isotropic without hydrogens. We just refine it by clicking on this old symbol. The camera is right in front of my. Carsten, lass es passt schon. Okay. Good. Yeah, passt. Yeah. We click on calculate maps, enable a difference map. Thanks, Carsten. And you see what is going on. So you have here the first orientation of your moiety, and the second orientation will be this one here. Zack, zack, zack. So this simple thing we will now model by hand. For this, there's two important Shellix commands you need to know. The first one is part, and the second one is the FVAR. Yeah? Part describes disordered parts which do not bind to other parts, and FVAR are free variables which you can use to refine occupancy or other things. It's a bit of a concept you need to get used to. If you understood how it works, it's super powerful. So I love it. Yeah. So the first thing we need to do is I want to give it proper names. So I click here on the naming tool. That's this NO thing. I want to put my atom in the first part. I want to tie the occupancy to a free variable, then the variable 2. And I always want to give the atoms of the first part the suffix A. Yeah, helps me to orient. You can also do it in a different way, but that's what I do. It will automatically increment now. So if I click an atom, it will be called C1A. The next one will be called C2A. So this is my C1A, my C2A, C3A, C4A, C5A. And this one here, this guy here is a nitrogen. And I call it N1A. So and I can close this one. And then you already see what Shellixlet did. It created part. So this is one disorder part with the names, and put here a 2 instead of a 1. That means the occupancy is now connected to the free variable number 2, which is up here and set to automatically to 66.6%. And now we can already refine. We click here. And it improves already a bit. The positive density is gone here. The too much model density is gone now. And it sharpens the remaining density here. So now we can clearly see the second orientation of the orientation of the second moiety. And now what we have to do is pretty easy. Again, you go on the naming tool. And now I don't want to have the suffix A, I want to have the suffix B because it's the second part. I want to put it to part 2. It's not part 1 anymore, it's part 2. And I want to tie it to the occupancy 1 minus the FVAR, because in total it has to be 100%. So there's no need to refine them separately. You refine only one and the other one is 1 minus. And then I start clicking again. So this is my 1C1B. C2B, C3B, C4B, C5B. The N I don't click because I don't want to rename it. It's the same for both parts. So I just copy it over. Like this. Add here the -2. And for me, I give it the name B. It's just a name. It has no relevance for the refinement. Okay, so you see up here in the FVARs, it's still only 1 parameter because the second part is 1 minus. You can now switch on part, let's go save it. You can switch on part highlighting up here, and then you see the 2 orientations. Yeah. There's no point, so there's a really rigid bond here and an orientation. There's no point why this nitrogen should have a different occupancy, a different ADP or a different position for both parts. Yeah. So I use my chemical sense to make sure to decide that for both parts, nitrogen has to be in the same position. So I could say E, X, Y, Z. That means keep the following atoms in the exact same position, N1A, N1B, and E, ADP. Use the same thermal movement parameters for both atoms, N1A, N1B. That's it. And now you can refine it. And we are down now from 16% to 12% already. And that already looks really, really reasonable. Yeah. If you want to do a perfectly right job, and this is what you will also find in the papers, then you have to make sure, of course, that these bond distances are all the same, because it's carbon-carbon bonds are very rigid. Why should they be different for the two molecules? Then you could now introduce SADIs to keep them constant, and also the same for the CN bond. This depends a little bit on the philosophy. The model in the end should be chemically meaningful. If you refine those both orientations and they give complete different angles or bond lengths, that's not chemically meaningful anymore. So for this, you have to move to use your brain. Yeah, I don't want to type this in now because it's a lot of work. But what you have to do in principle is SADI N1A C1A N1B C1B N1A C5A and N1B C5B. That would keep all the N C bonds constant, and you would have to do the same for all the C bonds. Of course, you can also click them and right click and say, where is it? Add restraints. Yes, you can of course also do. Yeah. Good. Let's see where we get. We refine it. There was not much change because in this case, the disorder is so obvious that they all refine to the same bond distances. We can now add the hydrogens. The nice thing about the parts is it will automatically also put the hydrogens of the writing model in the right part. We refine it. And in the end, we make it anisotropic. And we get a very nice 3% structure out of it with very low residual density. And we nicely modeled the disorder. And this all looks quite chemically meaningful. Again, you need to check the bond distance, of course. Yeah, you're the final evaluation step. Okay, so that was how you deal manually with twins. I do not want to go through the whole processing to the final CIF now. I just wanted to show you how you manually reasonably model this kind of simple disorder. Are there any questions regarding this case? Not yet. So then let's wait maybe half a minute. In the meantime, I can also show a very nice other tool. You have up here in Shell Xlayer, you have the select part checkbox, which is easily missed. It selects all atoms belonging to a certain part. So at the moment, it's selecting part 0, so non-disordered part. And now it adds part 1 or part 2. Let's select part 2, only part 2. And now you can click here on this crossed out eye symbol. Screen is so far away. I don't see it at the moment. Ah, here it is. Yeah. Then it will only show this part. Or you take part 1 and hide the second part. And if you put your mouse cursor up here and use your mouse wheel, then you can toggle between the two orientations. Yeah. Moving the mouse wheel up and down. This is very nice if your disorder gets complicated. Let's assume you have a MOF where your metal center is disordered and your linkers are disordered. This is a very nice tool to get an idea whether the whole bonding situation still makes sense. Okay, since there are no more questions, I would proceed to the next example.
Question if you can repeat the last step, so showing the.
Absolutely, I can do that. So that was the starting point. That's our molecule. This here is the part highlighting, which highlights the different parts. There's this very nice checkbox up here, select parts. I used Shell for many, many years, and I missed it for many, many years. Christian showed me at some point. If you click that, it allows you to select parts. So now at the moment, only the part 2 is selected. And if you say now include part 0, it will now select part 2 and part 0, or here now part 1 and part 0. If you click up on here on this eye symbol, this means hide everything which is not selected. So you only see the main part and the first part. And if you put your mouse cursor now on this spin box here and just use the mouse wheel to roll up and down, you can flip through the display of the different parts. So part 0 with part 1, part 0 with part 2. And as said, if your disorder gets very complicated, this is a super good tool to keep an overview whether the bonding situation still makes any sense or not. Because if you have 5 parts and different parts for different moieties, it can be very hard to see whether everything is still okay or not. Yeah. If you want to bring everything back into the view again, you click on the eye symbol again, which means show all hidden. Yep, you're welcome. Okay, so then we go to the next example, which would be the training DSR. So what you would have to do is you say new sample, open it. On my computer, this already exists because we've given this workshop before. Again, what do we see? We go to work directory. We see HKL ins, and so the other files you don't see, ins, HKL, and the solution for cheetahs. Again, we do not have a look at the solution for cheetahs. We again don't process the data. We only solve the structure and try to identify the disorder and refine it. So you click on solve structure. It automatically loads the HKL and the ins file. The P4P file doesn't exist, no problem. The information is generated from the other data. So as long as nothing is read, everything is fine. It's a boron compound. We click solve. And you already see you get a very nice structure out of that. But this part here, this flat Flanders thing there, doesn't seem to be right. Yeah? P21ON is the right space group. We close the solution plugin and go to the refine structure plugin. We see here our solution. And the first thing I do is I just refine isotropically first. Yeah, it's a 16%, 17% structure. Obviously, this thing here is the problem. Yeah. I could ask you now what this is. Which would be pretty stupid because I showed it on my initial slides. It's of course disordered toluene. Yeah? And toluene is something which likes to do that a lot. Yeah, so whenever you have toluene in your sample, it most probably will look like that. Yeah, so it's a disorder, and you see some atoms are with intense colors and some are with faint colors. That's a nice thing in Christian's program, that it also shows the symmetry equivalence. So we can fuse and expand here. Okay, so what do we see? You can also grow the Q peaks. Okay, there's not much around here. So what do we see? We see here this flat thing. And if you look closely, this would be, for example, the first orientation of the benzene. And the other one is generated by symmetry. Yeah, the problem here is that this piece is disordered over symmetry center, so P21/N, so the inversion center is here. Yeah. So the twofold axis goes through there and the gliding plane, and the point where they intersect is the inversion center. So now we could again try to model that by hand. And if we have nothing better to do, we could of course try that. But this is something which would take a while. And here you can now make a lot of use of DSR, so the tool from Daniel Kratzer I mentioned before. You find it up here under under Tools, DSR plugin. You click it. Then, as always, it opens on the other screen. So it looks like that. And we have here a fragment database or solvent or fragment database where you can also define your own pieces. And what we want to look for now is for toluene. There it is. It's in the standard database, this one. So here you pick the database. Here you can look for it. Here's a preview. Here's some info. And what you have to do now is you have to fit this fragment onto the molecule of your refinement. For this, you have to define a pivot point, which means you have to define 3 points. In my case, it will be this, this, and this, which is here. Now I have to be a bit more careful. I think this, this, and this. Is that right? Well, let's give it a try. We want to put this in a part, of course, but we cannot put it in a part 1 because it's disordered over symmetry center. So the symmetry equivalent would be also part 1, which we do not want. We do not want to bind to the other part. And for this, we have the part -1, which frees the part from its symmetry equivalent. Yeah. We want to use a free variable. No, we don't want to do that because it's disordered over symmetry center. So it has to be 50-50. Yeah, so we keep it to the standard one, 1, and set the occupancy to 0.5. Yeah, it will not be refined. It's fixed to 0.5. And then we say replace target so that it removes the atoms which are already here. There are some additional options which I don't want to go through in detail. I just want to say fit fragment. And this is what you get. There's just one thing I don't like. This is this atom here, which is a remaining atom, which is just nonsense. Yeah, we remove it, save it, and then you see what we already got. Yeah, and that already looks pretty reasonable. Yeah. So now let's test whether it's reasonable. The ultimate test is, of course, the refinement. If it stays stable, it is okay. If it explodes directly in your face, then I did a mistake. It did a mistake. So I refine it. I click on this one. Apparently, no, that's all right. It should be 0.5, right? Yeah. Okay, 50% occupancy. Okay, now it looks better. Yeah. And you see that already looks pretty good. Yeah, so here's the symmetry center. It's disordered here over the symmetry center. So with DSR, this is modeled within, if I would not be talking and you would not have to listen to me, this is a matter of a minute maximum, recognizing, modeling it, making sure it's stable. Yeah. If you do that by hand, you will have some fun and would need a lot of time. Okay, by the way, putting 10.5 here is equivalent of putting it here. If you put it here, it will automatically copy it to all atoms in the part. You know, that's something which is quite helpful. Yeah. Now we do not refine the occupancy. Again, it's still linked to the free variable 1, which is the overall scaling factor. And it's therewith fixed to 0.5. Since there are no complaints in the chat, everybody is aware of that, which is quite good. Okay, so this order is modeled. Let's quickly finish now the structure. That, as said, that looks already reasonable. So we can enable the maps and have a look at the residual density. So this doesn't look right. It's a boron. And that one doesn't look right. It's also boron. Better? And you already start seeing the hydrogen atoms, and that is a very good sign. Yeah. So what we do now is we shall say automated hfix and refine it. You have to check whether that's all done properly. This is of course not right. This is a 137. Christian has a nice tool to add that one. Right click. Add this ordered. Add ordered. This one. And then the only remaining thing we have to do is make it anisotropic. And we are down to 5%. Okay. And now it's up to you again to check whether this looks reasonable. You see the ADPs get a bit elongated, of course, because the other one is overlapping. I personally would try to use some restraints here, like the Rigu, to make it more reasonable. There's no need here to check whether the bond lengths between the molecule and its symmetry equivalent are the same, because they're anyways generated by symmetry. You should just check whether the benzene ring distances, CC distances are the same. If not, I would use a SADI. Okay. So that already looks pretty good. There's one thing remaining. Check always for charge balance. If you properly check that, you will see that here's nitrogen missing. And not nitrogen, hydrogen. You can add it with a writing model or whatever, or with a defix just for finishing it properly. I would just put the hydrogen here, freely refined. I know that's something you shouldn't do, but just to make it clean. Refine it. And then we started at a 17% structure, and now we're down to 4.5%.
It's an interesting question. Which command is appropriate for placing hydrogens on water oxygen?
Water oxygen, you cannot use an H-fix because there is no fixed bond. You have two hydrogens and nothing. So there's no way for the software, there's no reference atom from which it can derive the orientation. What I typically use, I analyze, I check the hydrogen bonding network, because water is usually not free floating in the structure. It has a very strong bond. And what I usually try to do is, if I see the hydrogens, so if I see the density, I refine it. If I do not see them, I do not refine them, because then it's just vicious. Yeah, to have no indication where the protons are. If I see them, then I never refine the hydrogens freely. I always use defixes and tanks if necessary. And my preferred way to do that is going to the DSR plugin, which again loves to open in the wrong window here. H2O, there's water in there here. And then use this one. And in this, I use this to place it as a fragment. And if you click on edit, you will see that there are already the important defixes in. And so you don't have to do that by hand. So this is another valuable piece a DSR can contribute. Okay. I mean, it's one very strict rule in refinement anyway. Don't refine anything you don't see. And disordered water, I mean, a proton has only one electron, which is not at the position of the atom, but in the bond. And if you try to refine disordered water protons, that's fractions of electrons. You need quite good data to see that. Okay.
That's all for the moment.
Okay. Yeah. Everybody clear how DSR works? Shall I repeat that, or was it clear? I think there are good chances if I repeat that it will work again.
No complaints.
No complaints. No complaints is good.
Okay. There was one.
Can you repeat one more time? Sure. Let's solve again. Check that's the right files. I solved the structure again. So that's the solution, P21 over n. Obviously, this part here is nonsense.
While you're doing it, can you give more details about R minus 1?
Yeah, absolutely. Let's explain afterwards. Yeah. Okay, you see here this ugly Flanders thing, yeah, where we know already it is benzene. Yeah? And now, if we refine it once and see the Q peak, it's quite obvious that this part here is the ring, and this is the methyl of the first orientation. And this part here, it's one missing, that's the Q peak over here. This part here with this methyl is the second orientation. Here, that is the inversion center. Well, that's in this case, it's pretty easy because if you click here on fuse, you see that most of the part is missing. So this is, of course, over symmetry center. If it is not missing, then it's not on the symmetry center, and then it's on the general position, and it's not symmetry related. Yeah, I will come to that later. Yeah. Okay. In this case here, we now have, we will use DSR tools, DSR, Tolu in it, this one. And now you have to click 3 atoms here. Let's take this one, for example, and this one here. And then you say part -1. I will explain in a second. We don't refine occupancy, put this to 0.5 and say replace target. Yeah. Why part -1? If you put it to part 1, then also the symmetry equivalent will be part 1. And then you have bonds between both parts, which we do not want, because within a part, everything binds. Part -1 frees the molecule from symmetry. So it's allowed to move from symmetry fixed positions, and it does not bind to its symmetry equivalents. And that's exactly what we want. We do not want that the first toluene binds to the symmetry generated toluene. Yes, I will show it. So I leave it on part 1, fit fragment, and that's what you get. You get this nice pizza thing. Yeah, this is not what we want, because now the dark black binds to the bright black, so it binds to its symmetry equivalent. This is not what we want. Yeah, so we go back, so we can say here restore last freeze file. This again, and we can say part -1 fit fragment. I have to click it again. Yeah, thanks, Carsten. Fit fragment. That looks much better, because now you see this part does not bind to the symmetry equivalent. Here's no bonds. Yeah, we close it. This here is a remnant of the of atoms, which was not replaced, so we removed that. This is something you should tell Daniel. It doesn't put automatically the 0.5 here. Yeah. You see, its symmetry equivalents are not binding. So if you now click on fuse, it's gone. Yeah, completely. Yeah, and if you refine it, then you're there. Are you answering, Carsten, the question? Okay. I think also with this part it would work. I never checked it. Let's take part -1. Oh, no, it doesn't work. Does not work. Okay. Good. I think there's no point of going through the whole processing again of the refinement. I hope it is now clear how this DSR works. Anyway, the next example will also deal with DSR. Also a quite nice example. Yes, it looks for residuals, actually. Okay, good. Anything else on this example? I take this as a no. Yeah, the 147 takes the whatever O bond as a vector to rotate around, and then look at a certain angle, I guess the tetrahedra angle in a certain distance, which would be around 1 angstrom, for the highest density, and then puts the hydrogen there. And that's what Carsten means by it needs a bond as reference. Because oxygen is quite intolerant with this H bonding angle. Okay, good. I think that's all on this example, and I would again close this one. I can save it. Yes, exactly. Again, water has no reference bond. Water without hydrogen is only an oxygen. There's no reference. It doesn't know, has no reference where to put the hydrogens. Yeah. Good. Last example I want to show in detail is training ligand disorder. So what you have to do is you have to open a new sample, navigate to the ligand disorder example. And create a new one. I will just reopen it. Carsten, can you answer that? Okay, thanks. Again, we will have a look at the work directory. What you find in here is an HKL, an INS file, and a P4P file. And again, a solution for cheaters we do not want to use. We try to solve the structure again. We click on solve structure. It automatically loads the required file. So you see it's a cerium complex. We click on solve. A variety of different solutions. So this 2, so this is a larger one, 7%, and this one 8%. So R minus 3 is the right space group. I accept that and go to refine structure, and then I take a second to read the question. Do you want to answer via chat or shall I answer directly? Well, depends a little bit on the case. I mean, can you share that? Well, the symmetry related disorder, the disorder is the same. You just have the additional challenge that a symmetry element through your molecule can make it a bit more difficult to define the different atoms. Also, if an atom lies on a symmetry element, the occupancy is of course lower, because it's on a twofold axis. It's only half occupied because the other half occupancy is generated by symmetry. So I would really need to see this example to give proper advice. So maybe offline or after the meeting, you could share this with Carsten and me, and we can have a look and give proper advice if that's okay for you. Okay, good. So this is the molecule. Now it's a very simple complex. So you have here cerium. This is oxygen, not carbon. And you have here the phosphate or sulfate, I don't know. Can't remember. And benzene. Yeah, should be sulfate, I guess. Yeah. Okay. That looks okay. I'm happy with the solution. Looks pretty good already. I refine it. I get a 7% structure, which makes me very happy already. I look at the residual densities. So this is a bit positive. This is negative. Here, I change that to oxygen. Oxygen, refine it. It's a 6% structure. Already looks reasonable. What I like to do then is I go here to ShellX, automated labeling, label without residues. That's a new function Christian put in to automatically give good labels. So it's now properly labeled, not with the generic ShellX listings anymore. And yeah, that looks pretty good. I will now add the hydrogen atoms, refine it. Looks nice. I want to make it anisotropic, and I'm down to 5.4%. I could now refine the weighting scheme and call it a happy day. But we have here a residual density peak of 3 electrons. Yeah, you could now say, oh, the data was not too good, or the absorption correction is wrong, or whatever other excuses are usually used, or sometimes are they really true. But if you look really closely, you see one thing, and this is there's one very strong Q peak here, and there are 2 additional Q peaks here, which look very much from the geometry like this thing here. And on the sulfur, you have a lot of positive, so too much model density, which tells me this atom here is not fully occupied. And this tells me, since the geometry of these 3 Q peaks is the same as this, that there is a second orientation of the same ligand, yeah? Which would make to some extent also chemically sense. Yeah. Okay, how to model that? First thing we need to do, as always, we remove all hydrogens. That just makes life harder, and you can add them later on again. Second thing I do is I select all atoms. You can press Shift, Control, then you can drag this box, then everything is selected, and say make selected atoms isotropic. So everything is isotropic again. So I don't conceal any information. And if you look closely here, you also see here a ghost benzene stuck in this other benzene molecule. Good. And now we can start modeling. Of course, you can now do this by hand, which is pretty tedious and cumbersome, or you again use DSR. For sure, this molecule will not be in the DSR, so you have to define it yourself, and that is why I chose this example. So first of all, I get rid of all the Q peaks. Then I take, I select with this Control Shift mouse drag all the atoms which I want to create a model from, and then I go to Tools, DSR plugin. And then you just take any, doesn't really matter, and say Edit Fragment. You get this new dialog. And what you have to do now is you remove everything that's in there. Everything gone. And then you say use selected atoms, which does automatically the coordinate transformation. So it's already in. And then you give it a nice name. So in the last workshops, I always called it Tobias. So I called it this time Carsten. Now important, do not update the fragment because then you would override this. You say now add as new. You can of course also put in restraints here already. This as the first attempt, I don't want to do. Yeah. So I say add as new. Then you return the previous dialog. And if you now check, you will see that there is a Carsten fragment. And this is exactly the molecule just inserted. Yeah, you can, of course, export that and use it or import it in any other DSR on any other PC. Daniel also told us where to find the database file, so you can just transfer the file. If you're interested in that, just write Carsten or me an email and we can look that up. I just don't know where it is from the top of my head. Okay, So then we have our fragment. So what do we have to do now? Now we have to put this ligand into part 1, not the cerium. The cerium stays the same for both parts. Only this part, you can either do this by hand now. I'm a bit lazy, so I just click these 3 atoms here and click these 3 atoms, which gives a perfect match because that was the template for my model here. I send it to part 1, free variable 2, because I want to refine the occupancy, and say replace target fit fragment. So it looks exactly the same. The only difference is now that it's in a part and tied to the free variable 2. And now we refine it isotropically. Yeah. Looks good. So nothing exploded. Occupancy refines to 90%. So there's not a lot disorder, but a little bit. And this nicely pronounced is also now this additional Q peaks. With this here, you can add a filter, Q peak filter. I want to see them all. Okay, so to identify the second orientation. So here we have the clamp, this OSO clamp, and the first benzene ring lies on top of that one, and the other one is stuck through this one. So I now go to Tools, DSR again. Now you have to make sure you find the right orientation. So it's this in this case. I click the 3 atoms to define the point. Click the 3 atoms. And then it shows me how it would look like. Yeah. So it will fall on top of this Q peaks here, which looks quite right to me. I tie it to part 2, free variable -2. I don't want to replace anything. And I just say fit fragment. And now I have part 1 and part 2. And to make it more obvious, I can click here this part highlighting. It looks like that. And now we can refine and check whether it still looks okay or not. Yeah? So our value is 4% now. Highest Q peak dropped to 1, yeah, which is pretty good. And you start seeing the hydrogen positions, which is very, very nice. Okay, so now your chemical sense is again wanted, because you see this benzene ring here is not flat anymore. Yeah, so it's a 10% or 12% disorder. 12% of 6 electrons is not a lot. Yeah, so of course this can show some weird effects. So again, your chemical sense is asked here. Now you need some restraints to make these 2 molecules the same. You can either use same, which should work to some extent. I personally would make it flat, yeah, and I would add some SADIs. So I don't want to spend too much time with the restraints here. I just want to put in a flat underscore to refer to the residue car. Yeah, so that these disorder parts were put in a residue. If you put this underscore car, everything you write behind will only apply to this residue. Both are residues. And I will say it's flat, and it is C1, C1 to C1 to C6 most probably. Copy, and C7 to C12 most probably. Yeah, we refine. Yeah, it's getting flatter. And then, of course, what you also should add is SADIs. Yeah, so you can, of course, also do this in the DSR. I just do it here. It's quicker for me. SADI, Blödsinn. SADI car C1, C2, C2, C3, C3, C4, C4, C5, 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 C6. C6, C1. Too many typos. So they have exactly the same bond length, or almost the same bond length. Of course, you have to do the same for SADI car C7, C8, C8, C9, C9, C10, C10, C11, C11, C12, C12, C7. Of course, you also can add the 2-3 contacts, and I think I put a mistake in because that doesn't look too right anymore. Yeah. So there's really your chemical 7, 8, 8, 9, 9, 10, 10, 11, 11, 12, 12, 7. Yeah, could also use affix 66. So my point is here, you have to make sure the model stays chemically meaningful. Yeah. Maybe you should also add maybe the 1-3 contacts. Yeah, that would help, which would be then the SADI car, C7, C9, C8, C10, C9, C11, C10, C12, C11, C7, C12, C8, I hope. Yeah, that looks better. Yeah, or you use the affix 66. Yeah. Good. So again, here, it is really important that you think about the chemical meaningfulness of your model. Yeah. Daniel always says no disorder without restraints. I'm not that strict. I always say it has to be chemically meaningful. So there's a wider range of interpretation of that. But restraints are for sure very helpful. Okay, so that already looks, we can also add the other ones here. So that would be SADI car, C1, C3, C2, C4, C3, C5, C4, C6, C5, C1, C6, C2. Almost 1, 3, 2, 4, 3, C5. Let's see whether that's right. Yeah, good. That looks good to me. Next step then would be Shellix automated HFix. Refine. And then the last step is the anisotropic refinement. And you're down to 3%. So we were quite happy already about our 5% structure with the high residual electron density P. And now we did everything right. And we are down now to 3.3% and 1 electron per cubic angstrom remaining, which is pretty close to cerium. So that's absolutely okay. Yeah, it's a very heavy atom. And you don't have any problems explaining that if you want to publish that. Yeah. Maybe you have to take a little bit care of this with anisotropic ADP. This is how you would treat such an example. If you want to go a bit more crazy, you could also think now about the parameter to data. Data to parameter ratio should usually be above 10. You can visualize the output here, and it will tell you how much data, how many parameters, the ratio, and so on and so on. If you want to look through that in detail, yeah, you have to, of course, make sure you do not over refine things. Yeah, if you throw 10,000 parameters in and only have 3 reflections, of course, it looks good. Yeah. Okay, a restrain is nothing fixed. It just gives a corridor for refinements and kind of a pull to get it back. This does not reduce the parameters. Yeah. A constraint, of course, is putting an equal sign in the least squares matrix. So that reduces parameters. There was a question, can you please have a lecture on restraints? Yeah, this is, Carsten already said it's a good idea. Maybe you should really do that. Also a bit about the mathematical background, what these things actually do. Okay, because restraints are no fixed corridors. It's just kind of a pain function, which gets more painful the farther away you go from the optimum. Yeah, if you want to put it like that. Yeah. Okay. So I think this nicely showed how you can use this DSR to model even these kind of more complicated disorders. And I must say, in the beginning, I never used it. DSR, I didn't like it. But the moment I learned how it works, I use it for almost every structure. Can you restrain an angle to 120 degrees? You can use, or do you want to answer via chat? Yeah, I think you can use dfix and dang, of course. Yeah, D-A-N-G and D-A-N-G to fix the angles that it reflects a 180-degree angle. Yeah, maybe Carsten can describe in the chat a little bit better. Of course, what's always very helpful, if you point on any of these commands here in Shell Ixle, and if you press F1, then it will automatically open. Have to move it up. It will automatically open the web page. So I click on temp. It will automatically open the Shell Excel user manual at the corresponding section and explain what this command is good for. Yeah. So this is very helpful, and even I have to sometimes check things still. Yeah. So let's say on SADI F1, then it tells you what the SADI is, that you can add some standard deviation values, pairs of atoms, and it's explained what it does and how to use it. And that's quite nice, actually. And of course, you can also add restraints and constraints by clicking two atoms and saying add restraint, add constraint. I'm just more the keyboard guy. That's why I do it by hand. Yeah, but that's the nice thing about Shell Ixle. It offers both options, text editing or clicking. Yeah. Good. Now let's expand the structure a little bit. So that is how it looks like. For me, that makes chemically absolute sense. Yeah. So where this is upright, the other one has to be flat. Where this one is flat, the upper one has to be upright. And if you want to get a better impression again, we can again use the select part thing. Maybe it's oriented like this. Hide others. And then scroll through it. Yeah? I think that this helps a lot to understand the logic of the structure. Okay. Good. If you want to have a look on all the parameters and so on, the parameters that are refined, the data, you can always scroll through the listing. It shows here the data that's used, how many unique reflections for the different symmetries, blah, 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 blah. Then the refined parameters next to the atomic parameters with standard deviations, some info on the restraints, summary of restraints in the different cycles. So you see here, where is it? Oh, it's just too far away here. Rigodilo, flat, 12 flat restraints, the sigma and the deviation. So there's a lot of in this listing file. So it's sometimes quite interesting to read that. Okay.
It's one error or one question about ratio observed to unique reflections is too low. How to overcome it?
Well, observed to unique reflections. I mean, if you get such an error in Platon or CheckCif or Arpex or wherever you checked it, you can always click on the error. It's a hyperlink, and it directs you to the IUCR explanation of the error. Ratio observed to unique means that you have too weak data. To be honest, I measured a lot of very, very, very weak data, and I've never seen this error before. That means you have a lot of unique reflections, and all of them are very weak. You need check whether your unit cell is correct, because that sounds to me like your unit cell is far too big and you're integrating a lot of zero intensities. Yeah, so if your unit cell is, let's say, twice as big as it should be, then only second reflection has intensity and all the others are just noise because your cell is wrong. And this sounds to me like a case where this could have happened. Yeah, but again, I need to see it to give a proper answer. Yeah, because even for the weakest data, usually at least the low angle data has some intensity, so you shouldn't get this. I would say unit cell is wrong. If the unit cell is right, and it's really a case of ultra weak data, which I do not believe, then there may be some tricks to tweak the integration parameters. I don't know whether you explained that in the best practice workshop tomorrow. Did you mention integration parameters?
Yes.
Yes, okay. So maybe you should join the best practice workshop tomorrow, which is the same workshop Karsten and Pratap did today, and they will explain a little bit the advanced integration parameters. Yeah, so usually integration does a very good job, but for very rare cases, it's a little extra trick, yeah, which will not save the world, but make it a little better.
I mean, always happy to get the data and we have it.
Yeah. Okay, so there were not so many questions today, so we are basically through the main examples I wanted to show. I just wanted to show you a very quick example, which I leave you to do yourself. I don't want to show that today. I only show you the solution and where we started. And I think it's already pretty late for most of us. Well, not for us, but for the attendees. And if there are no more questions, we will close it afterwards. So don't be shy, ask if there's anything left. The last example I want to show is the training Azoline. Yeah. Let me quickly move this out of the screen. Okay. So I deleted it. Okay. No, doesn't matter. Okay, what you see in there is HKL and INS file. Again, we want to solve. You click on solve structure, and it's a just CH compound. You click on solve structure, and you get this rubbish. Yeah, the different solutions in PC, in P1, P21, and P21 over C. PC and P21 are of course subgroups of P21 over C, so this is the right one because they all give similar R values anyway. Yeah. And the same rubbish. So if you get a solution like this, you would immediately say this is complete nonsense. Yeah. This is, well, if you manage to synthesize that, cool. But of course, this looks like pretty much nonsense. Okay, first thing I would do is I would check whether my unit cell is correct. If that's correct, I would check whether my data statistics and the diffraction is strong and good. If that's okay, then it is not the data, it's not the unit cell. Then it has to, it's the only chances that it is something disorder related. Yeah? So we take that solution and refine it. And again, you can see, I want to go back to the text output. Yeah, the R value is complete nonsense. And there's already some complaints about XT and water, which are also not real. You see it's over symmetry center because these are faint gray. So there's a symmetry center in the middle, inversion center. And now it is up to you to find out what the molecule is and how to best do it. I will quickly no, I don't want to show it. I leave this as a training example for you, as a little motivation to deal with that, because that's something which is not too trivial. You need to play a little bit with that and really practice yourself. I can show you how the solution looks like. This one. Yeah. So this is the solution. Yeah. It's 2 molecules of azoline, so it's a 5-membered ring with a common bond with a 7-membered ring, disordered over this inversion center. So of course, it will be part -1 again. Of course, your occupancy will be 50% again. And you already see what the problem is. These atoms of the 5-membered ring and 7-membered ring, they overlap. Yeah. And these atoms here, they do not overlap. So that means you have double the intensity at this position, double the electron density at this positions than you have here. And this is exactly what you have seen in the solution before. These are smaller because there's more intensity, and these are bigger. So this is the last one here, this Q peak. These are bigger because there's only half the density. Yeah, and this I leave for you as a homework. And maybe if I'm a
Tobias, are you muted?
So give me a second. Carsten, kannst du mal schnell sagen, dass wir kurz warten sollen? Okay, I think now you can hear me again, right? Just a quick yes or no?
Yes, yes, yes.
Okay, so the microphone just went out of power. So as said, I will show this tomorrow. So I leave this as a homework for you. We can go through it tomorrow together, or you can contact me later on, or Carsten, and we can work on that. And if there are no more questions, I would call it a day. Carsten, is there something else I need to answer?
I was here is how can you check that the unit cell is correct or not?
I mean, this is very easy, and I can quickly show it with some example. Of course, on this training PC, we only have complicated stuff. Sample, reopen. So this one is good. If you index, yeah, you have to always check the reciprocal lattice viewer. This is the diffraction point space, and the grid reflects a unit cell. From theory, reflections must only sit at the intersection points of the grid, on the grid points. Any reflection which is not on a grid point does not belong to this unit cell. Yeah? So let's say you see something like this. You can orient it with F1, F2, F3. Great. Yeah. This is a correct unit cell because in all directions, the some are missing because they were not harvested, but there's no systematic things wrong there. Yeah. Let's say you find something like, let me create something artificial. Like this. If you see something like this, yeah, this is systematically wrong because you see there should be reflections, but there's nothing, yeah, because your unit cell is too big. Yeah. So this is of course reciprocal space, so it's reciprocal. Yeah. So it expects reflections here, but there are none. So if you integrate that, it will integrate here always zero intensity because your cell is not right. Yeah, your cell in the reciprocal space is too small, which means the real space cell is too big. Yeah. So for example, your cell is 5, 5, 10. But it should be according to this 5, 5, 5. Yeah. Or the other way around, if you have additional reflection lines in between, which are not taken care by your unit cell, so they do not belong to that, but they're systematically there and obviously belong to this periodicity, then your real space unit cell is too small. Yeah. So RLED is the best tool, and Kenji highlighted and that a lot during the twinning workshop. And this is where we discussed this already. So I can really just encourage you to visit the twinning workshop tomorrow, where we will talk about this. RDAT is the best tool to get a very quick idea whether your cell is right or wrong, independent of scores and histograms and whatever. Humans are so good with their eye with pattern recognition that you immediately see whether unit cell is right or wrong. Yeah. Okay, perfect. Yeah, but I didn't see the answer. Okay, then if there are no more questions, I would say we call it a day. As a final reminder, we will do the exact same workshops tomorrow again. So it's not a part 1, part 2 thing. It's a repetition to give everybody the chance to join each workshop. Everything is, of course, recorded, and we will put it on the web later for you to see it. Give us a little bit of time. It's live recording. We need to refactor it. So I guess in 2 weeks, we should be ready. We will keep the share open for 1 month more. We leave the data there. We put also our presentations there for you to practice. And afterwards, we will move the videos, of course, to a streaming platform. Okay, that said, I would say thanks a lot for your attention. Have a nice evening, and see you tomorrow for the talks and the workshops. Have a nice evening. Bye-bye.